I'm very excited to be here and give a presentation today. So I will talk about how to create generalist robot models. And as you already said, the first video that I want to start with is our Pi0 model that controls this robot here fully autonomously. So there's no teleoperation or something involved. And this is a mobile manipulator that solves a very hard and very long horizon task. So the robot first goes to this dryer, unloads the laundry from the dryer, and then moves to this table and then starts folding laundry. This is an uncut video, and here you can also see the robot struggling a little bit, but eventually it will get it. And this task is very hard for many reasons. On the one hand, it's a mobile manipulation task, but it's very long horizon. So many things could go wrong, which could break the task. But it's also very dexterous. So folding laundry with two arms is a very hard task. And a lot of credit for this video goes to Michael Equi, as a research scientist at Physical Intelligence. Today, I want to talk about how did we create this model and give some context of the journey of it. So if you think about LLMs and VLMs, one property that we are kind of used to now, and we have to really think about this, right? For a long time, machine learning methods were very narrow. They only worked in very narrow domains on small amount of tasks. But for LLMs and VLMs have shown us that there are machine learning methods that can solve a large variety of tasks and basically work all the time. I think it's very remarkable, especially their generalization capabilities. Of course, there's still issues where sometimes LLMs hallucinate or don't solve a task, but one could really say they more or less work all the time. But the state of the art in robotics is very different. So robots usually work on a limited set of tasks and show limited generalization capabilities. For example, they only work in one home, but not in another one. And so the solutions are very brittle. And at Physical Intelligence, we're a startup that tries to fix that. So our mission is to build AI systems that operate in the real physical world. And we want to build generalist robot models that work in every environment and also for multiple robots within the limits of the hardware. So basically, we want to bridge this gap between the generalization capabilities that we see in LLMs and VLMs to robots. And in this talk, I will share the journey, how we ended up there. So I want to start with how we can take the lessons that we've learned from LLMs and VLMs and transfer them into the embodied domain. So the first project I want to talk about is Palmy, which basically took an LLM and put it onto a robot. But one disadvantage of Palmy was that the outputs of Palmy was strictly text. So then I want to talk how we then even further make this model more of robot policy, which outputs low-level robot actions. And I will talk about the Pi0 model, how we built that, how we trained it, what the architecture is. And this model was the one that controlled this robot that we were seeing in the beginning. Okay, so I want to start with Palmy, an embodied multimodal language model, which we did at Google DeepMind with wonderful colleagues. The idea of Palmy is to take a large language model and endow the language model itself with the capability to perceive the world by mapping other modalities such as low-level state information of the robot or images directly into the language model, such that now the combined multimodal model can make more grounded decisions about the world. And we train Palmy on a mixture of general vision language tasks and multiple robotics tasks at the same time. And by doing so, we get a model that can control these multiple robots, and we see very interesting generalization capabilities. And maybe the most exciting thing about Palmy was that we were seeing positive transfer, meaning that by training a model on many tasks at the same time, and especially also on these general vision language tasks, we got a model that worked much better compared to a model that was just trained on robotics tasks. So now let me explain maybe a little bit more what the motivation for Palmy was. So let's say we want to solve a robotics task of like putting this yellow block onto this blue spot. We can frame this as giving a model a goal and maybe an observation, and then we want to have a plan. And we think about this, such a plan looks kind of like text, right? So we could think of like how to move the yellow block on top of the blue plate and ask an LLM, and then we might get a plan in textual form of how to do that. But it's kind of clear that we somehow need to tell the language model about the state of the world. And maybe you could think of giving a textual description of the scene, but it's very questionable if there are generic actionable scene descriptions in text form that convey especially the fine-grained details. And the example that I like to give is this one here. So it might be very hard to describe this scene and where all these objects are in text. So the idea of Palmi was that instead we can learn an encoder which maps the raw sensor informations directly into this model so that this encoder can basically figure out what are the details that need to be conveyed to the model to solve this task. Our research questions were, how can we build such a multimodal model for robotics, so for embodied reasoning and planning? And what happens if we scale up? So if we scale up the model size, we scaled this model up to 562 billion parameters and to a lot of robot data and general VQA data. How does Palmi architecturally work? So it's very simple. So we start with text, put it through a text tokenizer, which then embeds it into a high-dimensional embedding vector, which is then fed into the self-attention layers of a large transformer. And then this model will auto-regressively decode text. So this is how most LLMs work these days. And then the idea was, okay, we take an encoder, which could be another neural network, which maps an image into the same embedding space, so with the same dimensionalities as these text tokens. And so then we can basically just place images arbitrarily in the text, and this way created a multimodal model. Palmi was trained on 3 different robot embodiments, so on a task and motion planning domain, on some tabletop pushing scenario, and a mobile manipulation domain. And the mixture, actually, the training mixture, only about 9% of the training mixture was robot data. The rest was general VQA data, and the majority of it was image captioning data and also VQA data. And then if we do that, we get a model, a single model that could solve all these. So there's the same checkpoint that could solve all these tasks at the same time. And we got very interesting generalization capabilities. So for example, here, we see a robot that's being tasked to bring the rice chips from the drawer, and Palmi here is running in a closed loop, so that, it's trying to grasp this here, but then there will be a disturbance, and because the model actually looks at the scene all the time, it realizes this and replants. And similarly here, so the robot is pushing objects around, but then someone puts an object again in the middle, and that the model recognizes this. But the most exciting thing about Palmi, which I think really changed how a lot of people thought about this, was the story of positive transfer. So what you see here is the performance of Palmi if you train it on individual tasks, and the performance is not that good. But now if you train one model on all of these tasks and on all of the web data at the same time, we got a huge bump in performance. Palmi was also a competent general VLM model, which got good benchmark scores at the time, although this wasn't even our priority back then. And to just give some qualitative examples, so the same checkpoint that could solve these robot tasks, you can also just ask general VQA questions, which we are probably all accustomed to by now, or more something like more roboticy. So given this here, what was the task? And this is the answer of the model, put all the blocks in a horizontal line. In conclusion, Palmi, we showed that we could frame embodied reasoning as vision language modeling, and we put a really large VLM model onto a robot, and we saw, by doing so, transfer between the robot and general VQA tasks. However, one disadvantage of Palmi was that it just output like these low-level subtasks, but it required on controllers that turn these language commands into actual robot motions. Let's think about the architecture of Palmi again. Is there a way that we can turn this into a policy that actually output robot actions, meaning like the joint movements of the robot? And the idea is very simple. So we can take a robot action, which is, let's say, a d-dimensional vector, and put it through some action tokenizer. And this tokenizer can literally be as simple as just binning the dimensions in discretizing and binning the dimensions of this vector. So now we just represent a robot action as a sequence of numbers where each number represents one dimension. And by doing so, we've basically turned learning a robot policy into a vision language modeling problem, because this is now just text. And this is exactly the idea of RT2, which we did at Google DeepMind, where we introduced this concept of vision language action models. So what can RT2 do? So we train RT2, again, similar like Palmi, it's also the same architecture. We train it on a mixture of robot teleoperation data. So we use 67% of robot teleoperation data, where we translate the robot actions into text. But then a third of the mixture was also, again, general vision language data. And by doing so, we saw something very remarkable, namely that we suddenly saw much, much better generalization in robotics, especially to unseen objects, unseen backgrounds, and unseen environment, compared to models that don't use a VLM as a backbone. And then what could RT2 do? So RT2 could do these semantic generalization tasks. So you could ask it, pick the extinct animal, and then it would pick this one here, or pick the lion, it would pick this here. In these examples, there was no data in the robot mixture that had any extinct animal or any lion in it. So this is really an out of distribution test. What we show with RT2 is, and here you see some more numbers showing more generalization results. What we really show with RT2 is that we can transfer internet scale semantic knowledge into robotics. And that, at the time when we did it, was really remarkable, because that was basically the first time that we more or less saw this transfer of other data sets that had nothing to do with robotics into these robot action data sets. But however, one has also clearly to say that the generalization that we saw was mostly semantic pick and place. So the whole thing wasn't very dexterous. So this is not a very dexterous task, especially if we compare it to the laundry video that we showed in the beginning. And then there was work by Tony showing that if you wanted to learn robot policies that are very dexterous, so for example, that can fold shirts or something, one key ingredient of this was to predict action chunks. So not only the next robot action, but a whole trajectory of up to 1 second of what the robot should be doing. So what I want to talk about next now is Pi0, the model that we built at Physical Intelligence that solved this task that I showed in the beginning. And I want to explain how we did this and what our goals were. So our goal was, okay, how can we take the lessons that we learned from RT2, but now do it for long horizon dexterous tasks. So the dexterity aspect, so we want to solve much harder tasks than just pick and place, while making sure that we have fast enough inference. So if we do these dexterous tasks, we need a model that is fast enough at inference. And also we want to train, again, a generalist robot model that works on multiple embodiments in multiple tasks at the same time. One of the main ingredients to make Pi0 work was actually a novel model architecture. So what you see here is basically the backbone of Pi0 is a pre-trained VLM. And Sophia, you said in the beginning that there will be some summit about Gemma. So the backbone of this model is a Gemma model, and we use the cyclip encoder to encode images. This architecture here looks very similar to Palmi and the RT2 style architecture. So we basically take images, encode them into the language space through a vision transformer, and also feed in the language string. But now, instead of autoregressively outputting robot actions, the key ingredient of this Pi0 model is to introduce a new set of weights into an action expert. How does this work? So if you think about a transformer, when you put an embedding in, it goes through the attention mechanism and then through the NLPs, and the different tokens talk to each other in the self-attention mechanism. And what we do now is if we have a robot token, so for the action expert, those tokens go through a different set of weights. So they go through a different set of key value projections, because after this projection, the dimensionality of both, we choose this so that the dimensionality is the same. So now the robot action tokens can attend to all those tokens at every layer of this transformer. This set of weights, we drastically reduce the size of the MLPs in this transformer, so to make it much smaller, 300 million parameters instead of 2.6 billion parameters. And then what this action expert is doing, it is predicting a robot trajectory. So each of those A's here is a whole one robot action. And so this is a whole robot trajectory. And this is being formulated as a flow matching objective. So at inference time, we run one forward pass through the backbone, and now we denoise basically noisy actions to get a robot trajectory, and this is run in a loop. We do 10 denoising steps, and this action expert attends to all those tokens here in the backbone. How do we train this model? So we train Pi0 on many different robots. So we have bimanual and single arm robots, and we have mobile manipulators with 2 arms. And the data mixture, so the majority of our data was actually from bimanual tasks. And then we also added in the open cross embodiment data as well. And this data set was around 903 million time steps. And I can't be sure, but we believe that this was one of the largest robot training experiments ever attempted. So, and if we do that, what we see is that we get a policy that works much, much better compared to, for example, the OpenVLA baseline. OpenVLA is a normal RT2 style baseline, and also like other models like Octo. So one thing that you really should take away from this is in order to make Pi0 work, we had to invent this architecture. So it was not just about scaling up data or something. We tried to make this work with other architectures. Other thing which was very insightful and in our investigation is the story of fine tuning. So what we show here is the performance of Pi0 when you run it after pre-training. So after we train it on all these tasks at the same time. So this is this here, this bar, versus if we then fine tune on individual tasks. So we can see that the fine-tuned performance is actually drastically higher than the pre-trained model out of the box. So this is something that we still have to address. This is the laundry unloading that we've seen already in the beginning. And you should really look at the details. These tasks are really hard, and they're very long horizon. So if you mess up at one stage, you can mess up the whole chain. And this is it's an uncut video. This is the laundry robot that we have seen before, but we can also look at other tasks. So it's the same architecture, fine-tuned from the base model. And this is a scooping task. And these tasks are all very significantly different from what we've seen in robotics, let's say a year ago. Or this task I also like quite a bit. It's building this box. It's also quite intricate and delicate. And these policies run in real time, so we can, if you change the environment, it will adapt to it. So I want to maybe give some more insights on why this architecture was really crucial and why we did not just do the RT2 style VLA. I said before, there has been a lot of research showing that this action chunking is required to make dexterous policies work. But if you did action chunking with the naive tokenization approach, then you would have to predict 700 tokens for a 50 Hertz biome robot if you predict an action chunk of 1 second. And this is not only very slow at inference time, especially if a multi-billion parameter model that you now have to decode autoregressively for 700 tokens, but also what we figured out is, or we had a really hard time trying to learn these models actually. So if you do this naive tokenization scale for action chunking, the models just didn't want to learn that. The last project that I want to talk about is very recent. So we actually came up with a tokenization scheme led by Carl and Kyle called FAST, where we figured out how we actually make it possible to train VLAs on high frequency action data. So how does this work? So what you see here are 2 dimensions of a robot trajectories. Think of it like 2 different joint dimensions over time. So this is the time dimension. So this is a robot an action chunk. So those 2 are 2 dimensions of an action chunk. And we take this and apply a discrete cosine transform on each of those dimensions individually. And discrete cosine transform is really just a function that maps n-dimensional vector to an n other n-dimensional vector. Discrete cosine transforms are, for example, used for JPEG compression. So what you get out is you basically now, instead of getting the frequency components of these signals, so you get different frequency coefficients, starting with the lowest one that basically just describes the rough shape of this curve, and then the higher frequency components, the more detailed. So now, given those components, we quantize them and bin them. And by doing so, what is very nice is we now get a lot of zeros. Discrete cosine transform puts the most important information in the low frequency components, where they are then not zero, but then basically through the quantization, the higher frequency components become zero due to rounding them. And so now basically we've turned a robot action chunk into this sparse frequency matrix, and then we flatten it. And we flatten it in a way by taking the low frequency components first. So in this flattened vector, the low frequency components, which are kind of the most important ones of the different dimensions, come first. And then we apply a byte pair encoding. So a byte pair encoding really just looks at commonly occurring pairs of these numbers and squashes them together into a new token. And what this byte pair encoding is particularly good at is squashing all these zeros. This is in this matrix. And by doing this, we've basically now tokenized action chunks into a sequence of these numbers much more efficiently. So if we compare for this shirt folding robot, we would need 700 tokens for the naive tokenization, but with this fast tokenizer, we only need 53 tokens, which is a huge compression ratio. And then if we do this, now suddenly autoregressive models can also work on this shirt folding task. So the naive tokenization literally doesn't work. We're not able to make it work. But with this fast tokenization, it actually now works. And if we compare this model to Pi0, on average, I mean, there are some differences which we could discuss or not, but like on average, they more or less can do the same thing. It is still the case that the Pi0 fast model is slower at inference time, so the motions of the robot look less nice, but it can achieve the same or it's very similar performance. And what is very nice about this is we found that using this, we can actually train much faster. So by using this Pi0 fast model, the number of training iterations that we need to train the model to achieve a certain performance is lower compared to this with the flow matching and action expert architecture. And one thing I want to show is, so there's the DROID data set, which is a robot data set. It was collected in many different locations all over the world. And people have always struggled to train a model on this data set, on all of this data set. And we trained Pi0 fast on this data set. And now actually, so these are evaluations at different locations done by different universities. Thank you so much for doing that. The model, you basically just put it into a new environment and will start doing something. I mean, these are simple tasks, but this shows that we can train a model that works in novel environments quite well. So before I want to conclude, I want to thank all my colleagues at Physical Intelligence. We are really a very strong and very good team and very friendly. It's a pleasure to work there. What have we talked about today? So I started talking about how we can take language models and make them into a model that is useful for robotics by outputting high-level language commands, and this model is trained on both robot data and general vision language data. And then we have talked about how we can now go even further and make a model that predicts robot actions directly low-level robot actions. So we've shown that we can transfer semantic internet scale knowledge into this model. And then we've talked about how we built the Pi0 model that then basically can make a huge leap in terms of dexterity and solve these very long horizon complex mobile manipulation tasks. And finally, we've talked about the novel action tokenization scheme that allows to do similar tasks that we've done with the Pi0 model with a vision language model in a more normal way. With this, I would like to thank you for your attention.